Hi friends, in this video we are going to see the last theorem in our DC circuit module, and that is maximum power transfer theorem. So let's say the statement of it first. It states that the maximum power from a source can be transferred when load resistance is made equal to the internal resistance of the source. So let's see what it is talking about. So first of all, it's very good if I know what is the maximum power that I can be getting from a voltage source. So for that some condition need to be satisfied, and that condition here they are stating as load resistance should be made equal to internal resistance, or you can say source resistance. So let's see the condition. So what we are going to do over here, we are going to see the derivation of maximum power transfer. So let's consider a simple practical voltage source whose open end voltage is V and a small series internal resistance, that is R. So this is a voltage source. So it's a practical voltage source. So for this voltage source, I am connecting a load resistance RL, and it is a variable one. That means I can change its value. So I will write all the notation once again. V is the open end voltage, R is internal resistance of voltage source, and RL is the load resistance. So let's derive condition for maximum power transfer. I want what is the power transferred from source to load. So for this I should know what is the current taken by this load. So first of all I will write expression of IL. So IL will be equal to voltage V divided by total resistance in the circuit. So it is V upon R plus RL. Now power transferred to load resistance, I will use a notation PL, simply given by IL square multiplied by RL. So if I substitute the value of IL, I will get PL as V square divided by R plus RL the whole square multiplied by RL. I will consider this as equation number 1. Now what I want, this power should be maximum. So I want to maximize this function, but what is the variable over here by virtue of which I can get this as a maximum? So for this we need to check the circuit once again. In this circuit voltage V is fixed, its internal resistance R is fixed, only variable is this load resistance. So actually I want to get a power maximum by varying RL. So this will give me a hint of maxima minima. So what I will do here, I will write an expression for getting maximum power. So to get maximum power transfer, I will differentiate equation number 1 with respect to RL, because RL is our variable. So, I will get dPL by dRL as differentiation with respect to RL V square multiplied by RL divided by small r plus RL the whole square. We know the concept of maxima minima. For maximum power transfer, this derivative should be equal to 0, means this derivative should be 0. So, let us differentiate this. V square is a constant, I will take it out, and here it is u by v rule of a derivative, which say v multiplied by derivative of u minus u derivative of v divided by v square. So, it is r plus RL whole raised to 4 equal to 0. I will take this term to this side, it becomes equal to 0. So, it is r plus RL the whole square. Derivative of RL with respect to RL is 1. Now, derivative of r plus RL the whole square is 2 into r plus RL into derivative of r plus RL equal to 0. So, what I am getting over here now? R plus RL the whole square minus 2 times RL into r plus RL, and derivative of this term with respect to RL is 1. Derivative of R is 0 because it is a constant, and derivative of RL with respect to RL is 1. So, from this expression I can take R plus RL common. So, I will get R plus RL minus 2 times RL equal to 0. Again I will take this to other side, becomes equal to 0, and finally I will get R minus RL equal to 0, which ultimately implies load resistance should be equal to internal resistance of the battery, or you can say voltage source. So, here I will write load resistance equal to internal resistance of a voltage source. So, I am getting a condition which we called as condition for maximum power transfer. Now, what will be the value of this maximum power? For that, we need to substitute R equal to RL in equation of PL. So, equation of PL is like this: V square divided by R plus RL the whole square into RL. So, if I substitute RL equal to R, I can get equation as V square multiplied by R divided by R plus R the whole square. If I simplify, I will get V square multiplied by R upon 2r square. So it is v square into r multiplied by 4r square. 1 r get cancelled. So I will get power transfer to a load from a source is v square divided by 4r. So every source has its capacity to transfer a maximum power, and that is given by its open end voltage square divided by 4 into its internal resistance. Now how we are going to use this while solving a problem? So for that, let us go back to a Thevenin's theorem. In Thevenin's theorem, we draw Thevenin's equivalent circuit, which is having a voltage named as VTH and a resistance in series with VTH that we named as RTH. Now these are the terminals A and B where load resistance can be connected. If I compare this with this circuit, I will come to a point where I can say this VTH RTH is nothing but a voltage source. So I will consider this part as a practical voltage source. Where VTH is open end voltage and RTH will be internal resistance of voltage source. So now I can say what should be the resistance connected between terminals A and B, which I can say load resistance, so that maximum power will be transferred through it. So for that, the condition is your load resistance should be equal to Thevenin's equivalent resistance, which is a condition for maximum power transfer. And what will be that power? Is nothing but VTH square upon 4 RTH. This is expression of maximum power transfer. So what we have done, basically maximum power transfer theorem is just a application of Thevenin's theorem, where you have to get the RL, which is nothing but RTH, to get maximum power transfer through it, and the expression of that power will be VTH square divided by 4 RTH. So it is just a extension of Thevenin's theorem. So whenever we will solve a problem, at that time we will come to know the procedure is absolutely same as Thevenin's theorem, only added feature is this expression. So in subsequent videos we will solve numericals based on this. Thank you.